Starting to record? Sanjay? Yeah. Okay.
Yes, sir. Started, sir.
Okay. Okay. So last class we are mentioning that we assume inviscid flow and neglect heat conduction effects in Navier-Stokes equations with no source terms. We get the Euler equations. Further, if you assume the flow to be steady, irrotational, incompressible, and two-dimensional. Okay. Irrotational is del cross V is 0. Okay. Not incompressible. Irrotation means del cross V is 0. Then if del cross V is 0, then mathematically we are assured of the existence of velocity potential. We are assured mathematically that then V is equal to del phi. V can be expressed as del phi. There exists a function like that, phi. All you need for this V to be del phi is the del cross V should be 0. So that is flow to be irrotational in fluid dynamic parlance. So for such flows, equations of motion reduced to the famous Laplace equation to velocity potential or the stream function. So del squared phi is 0 or del squared psi is 0, where phi and psi are orthogonal to each other at every point. Now the advantages of potential flow are the governing equation is linear, so only one equation is there. These are coupled nonlinear equations. So because the governing equation is linear, we can add basic solutions and the sum will still be a solution of the Laplace equation. Usually obtain solutions for uniform flow, source, sink, and vortex flows. Doublets are also included. Doublet is actually a combination of source and sink. So you can add them to this. You can consider them elementary flows, although sink and source are more basic. Then we can add these basic solutions intelligently to create more complex flows. So we look at these basic solutions in the next slide. So we immediately jump to the panel methods. I'm also giving only an overview here given in Anderson's book. So 2D potential flow solutions for velocity potential given as m by 2 pi into ln of r by r naught. Vortexes phi is gamma by 2 pi theta. Then uniform flow in the plane, the phi is ux plus vy. Polar coordinates we saw yesterday. So we also saw that streamlines are lines of constant stream function. Across it there is no mass flow. So for stream function to be defined, already we are implying that flow should be inviscid and irrotational. So don't think that streamlines in viscous flow will have the same effect if you replace these streamlines by solid walls. Although there won't be any mass flow across streamlines, the effects inside this will be different if you have walls and the flow is viscous. That's what I was telling yesterday. So you might have created these complex flows either in a fluid dynamics course or in the aerodynamics course. Okay. So image of source and sink separated by finite distance. If you place it in uniform flow, you will get flow over an object called Rankine oval. Then if you have a source and its image, or two sources placed together, will form a straight line. You can actually have the other one as an image, and you can find the source placed near a solid wall by this method. All you need is simulating a straight solid wall boundary, just done by placing a source and its image together. If you have a source, have another source of equal strength. You have a solid line in the middle, the line joining these two. Similarly, wall boundary can also be formed by a vortex and its image. We have vortex of in this anti-clockwise direction. Here you have the vortex in the opposite clockwise direction. You will get a streamline here where velocity is the downward direction. If you reverse them, the velocity is upward direction. But this will be for all practical purposes. You can treat this as a solid wall. So there are two methods of creating a solid wall, but the method is slightly different. If you create it by a source, the direction of velocity will be upward in the top half and downward in the bottom half. If we replace them by a sink, okay, then it will be downward in the top half and upward in the bottom half. If you have the vortex, it will have either downward all the way or upwards all the way. You can also put a uniform stream. So you put a source inside a uniform stream. You can simulate a semi-infinite body. You might have done that earlier. Then we have seen what is a doublet last class. Source and sink placed at an infinitesimal distance from each other. It's called a doublet. If you place a doublet in free stream with the source set upstream, okay, not a doublet, a source and sink, upstream or downstream uniform flow will give elliptical cylinder or Rankine oval. This is a Rankine oval shape. If a doublet is in uniform stream, you get a flow over a circular cylinder. Okay. So these are the basics of potential flow. Then you would also have studied about vortex panel method. So what do we do in vortex panel method? We replace the airfoil with a vortex distribution. Each distribution you can consider as each vortex. You can consider it as uniform along a small segment. In other way, divide this airfoil into small straight line segments. Assume that you put a vortex in the center of each small straight line segment, and assume that the strength of the vortex is same for this small segment, which we call as panel. Okay. So now what you do is you apply the boundary condition that velocity should be tangential at airfoil surface or tangential to all panels. Okay. Now how do you find that velocity? You have the potential for the free stream phi. Then assume that the potential of all this is unknown. All these are known. In other words, consider them as vortices, small, each one to be each panel replaced by a vortex of strength gamma 1, gamma 1, gamma 2, gamma 3, and so on up to the gamma n. Okay. Each of this will have an influence at all the points in the flow field. So, for example, at any point, it will be influenced by this free stream and every one of this vortex. Since phi is a scalar function of x and y, you just need to add all the potential. You get the potential, potential due to all the vortices. Substitute the x and y for that location, you get the potential there. Then find dou phi by dou x, you get u component, dou phi by dou y will give you v component. Similarly, on the airfoil itself, you can select some points known as control points. On this control point, the flow should be parallel to the airfoil. So with this condition, you can form one equation which has the effect of all the vortices except that one in which it is situated by itself. That will have a separate There's a separate formula for that. So you add, anyway, whenever you are adding the potential due to all the vortices and the free stream, you get one equation at a control point. If you have n control points, you have n equations. If you have n vortices, you will have n unknowns. Okay. So n vortices, n unknowns, you can find the strengths of all these vortices. Now, what if you find the strength? If you find the strength, then you can back calculate. Using that strength, you can find the potential at every point. By differentiating the potential, you can get the velocity. By using free stream pressure, you can get the pressure distribution at all the points. So finally, if you get pressure distribution, you get CP distribution, you have lift, moment, and drag. All three are. Basically, you can solve the whole problem. There's a small catch here. At the trailing edge, usually we try to ensure that Kutta condition is satisfied. So actually, on the trailing edge, the gamma should be 0. Okay. So we impose this by telling that the strength of vortices above and below, on the before above the trailing edge and below the trailing edge are equal and opposite in sign. In the sum at trailing edge, the gamma will be 0, which will ensure that the Kutta condition. Okay. Now you would have read the proof for all these things in aerodynamics 1. This puts one extra equation. You have n equations, n unknowns. Now n unknowns, but n plus 1 equation. So you have to consider, you have to drop one of these equations. You have n unknowns and n equations, you can solve. You have n plus 1 equations, you have an overdetermined system. Okay. So which one to drop is a good question to consider. Depending on the problem, you can drop one of these. What I would suggest is, if you have actually no suggestions, but if you have a very flat region, probably you can select one of those vortices and replace it with the Kutta condition. Okay, just like the vortex panel, you can have source panel method. Then if you use doublets, you can have doublet panel method, and so on and so forth. When you say source, actually include sinks also. Usually, the source panel method, giving a very general statement here, the vortex panel method is good at estimating the camber of an airfoil. Okay, you go for slightly thick airfoils. With thin airfoil theory, you get this one. Vortex panel, the vortex panel method is good at estimating the camber and also the lift on the airfoil. The source panel method will actually be better at simulating the thickness of an airfoil. So you have even combination of this method, source and vortex panels. All kinds of very complex things can come. If you want to know more about panel method, you can ask Rajesh sir. He has done quite a bit of work on panel methods. We'll go to the next lecture. So it is just explains what I have been telling now. Vortex sheet is infinite sheet. You take a cross section. The cross section is shown here. Edge view of the sheet. You have done this in aerodynamics 1. dV is the velocity induced due to each one of these vortices and the free stream. Airflow is divided into several panels here, just straight lines. Then Kutta condition satisfied and those damage all panels, and the del phi due to each one is given here. How to calculate theta is given here. So choose control points, n number of control points. Calculate velocity potential at control point. So the free stream component should be normal to the right span. This is the boundary condition implemented at one control point. So the boundary condition V infinity n, the normal component of field V, plus the induced normal velocity should be 0. Total velocity, normal velocity should be 0 with the boundary condition and the solid one. So this is the boundary condition. Okay. So additional equation, Kutta condition is given here. Then you have to drop one other equation. Now we'll take a break before going to the next item. Yashas? Yashas? Is Yashas here? Dev Sultan.
Yes, sir.
Can share something.
In this lockdown, I started watching more of other language films like Malayalam and Telugu, and I did like them, sir.
Yeah, they're very good Malayalam movies. Then I do watch them. Telugu also I watch. Telugu, Malayalam I watch Nizal. Nice
Yeah.
movie recently.
What is that, sir?
It's a thriller basically. Not a very violent thriller, but not violent in picture, but the theme may be a little bit.
I'm not able to get you properly.
I mean, it's a thriller. It's a thriller movie. Very slow moving thriller movie.
What is the name of that, sir?
Nizal.
Oh, okay.
Nizal. What did you watch?
I watched more like comedy dramas and something like that. I
Oh,
didn't
okay.
watch any more thriller movies and something.
I see. Any titles?
I did like many, but
Hmm.
I'll have to search for that list, sir.
Just one will do. Some good one.
I would
Telugu
say
or Malayalam.
Jomonte Subisheshangal, sir. Dulkar Salman.
Uh-huh. Okay.
I like
Uh-huh. Okay. Telugu usually, it has a different style. We also watch Hindi, Telugu, sometimes Kannada also works.
I've not watched Kannada film, any Kannada film other than KGF. Sir.
I see. Some Kannada movies are really good,
Okay, sir.
but many of them usual masala stuff you see in Tamil anyway.
Yes.
Okay, thank you. Let's move back. The mathematical properties. What the mathematical properties or what? The governing equations. So we have finished the first two. Don't worry that you're going too fast or something. Some of these are easy, so we will cover fast. Some of these are complex, so we have to go slow. Errors and stability will take a long time. Generation transformation may take a long time. Basic schemes also may take a long time. So we'll go to this mathematical properties. There are two subdivisions here. One is how to classify them. Second is what do you call as well-posed problem? That is just a definition, nothing much there. Have you done this classification earlier in some other course? Sugandhan,
Yes, sir.
have you done this studies in mathematical properties of PDEs in earlier courses? Parabolic, elliptic, hyperbolic.
Fluids, we did some sort of.
Oh,
I don't
okay.
remember.
What did you do that? Huh? Anyone else?
Sir, we were just introduced to PDs in one of
Here
our
also.
previous semesters.
What did you learn there?
So,
Introduce means yeah. Here also only introduction. That's why I'm asking.
so we solved some basic models of PDs like heat problems,
Hmm.
something.
How do you say that it's hyperbolic, parabolic, or elliptic? Have you done that?
I don't remember that.
Sir,
Who's speaking?
sir, we have done b square minus 4ac. If it is less than 0, we call it as elliptical.
Yes,
Remember?
yes, exactly. That's all we are going to do here.
Equal to 0, it is a parabolic, and greater than 0, hyperbolic.
That's all we are going to do here also. Okay, nothing much. Hmm? So it's probably a revision for you. It's important for you to remember these things so that when revising things. So exactly what you have done. Take a general second order PDE of this form. Qxx is dou squared u by dou x squared, uxy is dou squared u by dou x dou y, uyy is dou squared u by dou y squared. Again, ux, uy are dou u by dou x and dou u by dou y. U is a function. G is actually a constant. So a general second order PDE can have all these terms. All multiplied by coefficients A, B, C, D, E, F, and G. So whatever be the values of D, E, F, and G, what determines the form of the PDE, the second order PDE. Okay, we are talking only about second order PDEs here. We can classify according to the sign of the term B squared minus 4AC, as Sanjay was telling. Now, interestingly, if you take the general equation of a conic section, so there's a general equation for hyperbola, parabola, ellipse, and also straight lines and point, but those are hidden. We consider them degenerate conic. They are subsets of this. If you put ABC 0, you get a straight line. If you put XY also 0, you get a point. So, sorry, DE also. So points and straight lines are subsets of this. So this is the most general form. If you want a circle, you put A is equal to C, then B, D, E is 0, and take F to the other side. Minus F is probably R square. So the sign of discriminant B squared minus 4AC determines whether the conic is ellipse, parabola, or hyperbola. If it's less than 0, it's ellipse, equal to 0 parabola, greater than 0, it is hyperbola. According to this, we classify the PDEs. Right. But the similarity ends here. Don't carry over what you know about cones to the, the conics. What you know about conics to the PDEs. The similarity ends here. So that is why they are named as elliptic equation, parabolic equation, hyperbolic equations. The similarity ends there. Don't carry the similarity to any other extent. Okay. Don't imagine anything more. So an example, the 2D full potential equation, which is inviscid steady irrotational flow, is detailed in the next slide. There's one eigenvalue method of classification also. Suppose you have two variables in second order. So if this set of PD is given by A1 ux plus B1 uy plus C1 vx plus D1 dy. Now this is first order in two dependent variables u and v and two independent variables x and y. This is equivalent to a earlier one. Okay, but the form is different. Now you can classify this also in a similar manner. Okay. If you define a vector, or in other words, you can call this a matrix also. W as UV, which is now a column vector. The whole equation can be compactly written as A1 C1 A2 C2 matrix into dou W by dou X plus B1 D1 B2 D2 into dou W by dou S0. Once you have done this, put K is the first one, coefficient of dou W by dou X, and M is the second matrix. I'm just giving this to you for a flavor. Okay. Now we can rewrite the above as K W by dou X plus M dou W by dou is 0. So pre-multiply by K inverse, you get dou W by dou X plus K inverse M into dou W by dou Y is 0. You call K inverse into M as a matrix N. Now without proof, we state that the classification of the system depends on N. If eigenvalues of N are all real, equation is hyperbolic. If they are all complex, equation is elliptic. And sometimes you cannot classify them and they may exhibit mixed behavior. Sometimes elliptic, sometimes parabolic, sometimes hyperbolic. An example is transonic flow, where there's a mixture of subsonic and supersonic regions in the flow. So in subsonic region, it will look like elliptic. Supersonic, it may resemble hyperbolic behavior. Then if you go to Navier-Stokes flow, even subsonic flow can be parabolic or hyperbolic or mixed. All the way we are talking of inviscid flow. Okay. So the viscous subsonic flow is not elliptic all the way. It can exhibit mixed behavior. In general, you can say even subsonic viscous flow is hyperbolic, but you can make it parabolic and have an approximation near the boundary layer. So you get something called parabolized Navier-Stokes equation, ENS equation. Now there is one more way to classify using method of characteristics, which we do for in a compressible flow. Have we done this? Yes or no?
Sir, sir just gave a brief intro about this. Like we didn't go into detail.
Okay. But you will study more if you go take hypersonic flow theory or something like that. Such courses will give you more. Probably we will teach there. Anyway, it's good to know the elements here. It's good to know the fundamentals of how they are derived and things like that. Okay, so what are characteristic lines? First, we begin with the definition of characteristic lines. We can classify using this method also. So these are defined as a set of imaginary lines in the solution space. We'll talk about 2D now. 3D will become more little bit more difficult to imagine at this stage. We'll go with 2D. 2D means it can be a one dimension in space and one dimension in time. It is equivalent to a two-dimensional space problem. So both of them will have characteristics. Both are two dimensions in our this one. We don't, for example, x and t, there are two variables, two dimensional. X and y is also two variables, two dimensional. We will think like that. Now we look at the problem of x and y here. And we define something called characteristic lines because the definition will help us later. So we define that they are imaginary lines in the space. They don't exist. You cannot really see them, cannot catch them or feel them. In the solution space for a PDE, any PDE, along which the flow variables are continuous. Okay, but their derivatives are discontinuous. So, is it possible to have some variables like that? You might have done in your this one here. Limits and continuity, right? Limit on the left and limit on the right, and the value there should be the same only when the function is continuous. Yes, that can be satisfied. But for a function to be differentiable, first of all, it should be continuous. And then the dy by dx should have a unique value there. If it has more than one value, there is, even if it's continuous, for example, there's a sharp corner, you can draw two tangents there. So dy by dx has two values there. You don't know what is the value of dy by dx at that point. So there, since you don't know the value of dy by dx, your dy by dx is discontinuous. Dy by dx cannot be determined. Okay, that's what is determined. There are lines. Okay, and every point in this line, suppose you can draw a line, and every point in this line, if you go along the line, the flow variables are continuous, but their derivatives are discontinuous. Okay, so now let's say the governing equation is given below. This equation is nothing but the full potential equation. I told you, we can convert everything to potential equation, and then this is not exactly Laplace equation, but these are basically your we'll go to the derivation during chapter 8 in this modern comparison flow. Here, the last two are basically du, expressions for du. Du is dou u by dou x into dx plus dou u by dou y into dy. Similarly, dv definition is dou u by dou x into dx plus dou v by dou x into dx plus dou v by dou y into dy. Now phi y is dou phi by dou y is v. Phi x is dou phi by dou x is u. If you substitute, make all these, you can, the last two equations can be framed. The first equation is nothing but the full potential equation. We make approximations to this, then we get the Laplace equation. How to derive this is a slightly long story. So this is for the earlier we assumed density as constant. Here this is for compressible flow. When you look at phi xx plus phi y is 0, we assumed A is infinity. A is infinity means it's an incompressible flow, correct? You remember that? Whom shall I ask this question? Yashas is still not there. Aditya is asked. Let me find some new questions. Ashwin Kumar.
Sir,
Do you remember?
mm,
What should you remember? For incompressible flow,
sir,
the governing equations dou squared phi by dou x squared plus dou squared phi by dou y squared is 0. That is the Laplace equation, correct?
yes, sir.
Now, if you take compressible flow, for compressible flow also you can write a potential equation. Similarly, but unfortunately it is not the Laplace equation. It's not even a linear equation. Okay,
Yes, sir.
but that equation is the first equation here.
Yes.
So basically it is the potential flow equation for compressible flows. Okay.
Yes, sir.
Now you have along with this two other equations. Now this is a matrix. If you consider the unknowns as, you know, Cramer's rule, anyone know? Remember Cramer's rule? Okay, here you consider the unknowns as phi xx, phi xy, and phi yy. Okay, Ashwin?
Yes, sir.
So you can write this as a matrix, correct?
Yes, sir. We can write it.
Some matrix into this unknown is equal to some constant on the right hand side. Right hand side is 0 du dv. Now what is that matrix? If you multiply the inverse of the pre-multiply by the inverse on both sides, you will get a solution, correct?
Yes, sir.
So that is what is Cramer's rule. Cramer's rule says the solution also can be found out. Simply, he is getting a shortcut for the same thing. If you want phi xy alone, which is phi xx will come here. Phi xy is the middle 0, then phi xy, there will be a 0 here. You replace the coefficients of this middle term, which is 2uv minus 2uv by a squared, and here it is dy, and here it is dx. Okay, the coefficients of phi xy. Replaced by the corresponding right hand side, 0, du, and dv. Okay, and form a matrix, same matrix. See, this first numerator matrix is what I was talking about. You want phi xy. In the denominator, you have the whole matrix, which is multiplying the unknowns. Correct?
Yes, sir.
The numerator, you replace the, for example, you want phi xy. You replace this middle column by the right hand side, 0 du dv. 0 du dv. Okay?
Yes.
If you do this, you will get phi xy. Expression for that.
XY, sir, that is.
Phi xy is dou squared phi by dou x dou y.
Yes, sir. No, sir, the term was small, so I can't see it properly.
Yeah, xy, correct.
Yes.
So you have something like numerator by denominator here. If denominator goes to 0, there is no solution.
Yes, sir.
There is no solution. Okay. Now, what if you purposely set, similarly you can find for dou xx, what you do, you retain this term here, but instead of these first three, you substitute the 0 du dv here. You'll get solution for phi xx. Then if you do it for here, you'll get solution for phi yy. Understood?
So only the numerator, sir.
Only the numerator. Denominator is same for everything.
Yes.
Denominator is that matrix. Now we are taking the phi xy case only. Phi xy can be determined like this using Cramer's rule. This is known as Cramer's rule. Okay. Shortcut to find this. This has numerator by denominator. Now phi xy can be, phi x is what? U. Okay.
Yes, sir.
So it can be taken as dou u by dou y, left hand side. Am I right?
This term is dou u by dou y you're saying to take.
Left
sir.
hand. We can
Yes,
also take, because if you take as phi yx, it is dou v by dou x.
Yes, sir.
Both are same because flow is irrotational. Dou v by dou y is equal, dou v by dou x is equal to dou v by dou y. Because the flow is irrotational. Otherwise, it's not true. So there is phi xy can mean two things. Either dou u by dou y or dou v by dou x.
Dou v.
Yeah. So for now, we can consider dou v by dou y. What is dou v by dou y? It is the derivative of u along the y direction. The gradient of u along the y direction. That is dou u by dou y. If this fellow is discontinuous along y, if this is discontinuous, then that means denominator should be 0. No solution.
No
Correct?
solution.
So
Yes, sir.
now we put the condition. What is the definition of our characteristic line? They are imaginary lines across which the derivatives are discontinuous. The flow variables are continuous. So we say that u and v are continuous,
Yes, sir.
but the derivatives are
derivatives
discontinuous.
Yes.
Discontinuous. So you put the denominator to 0. That is, denominator is same for all. Yes. Denominator d0, what does denominator have? Dx and dy. Correct?
Yes, sir.
And solve for the condition. What is the condition? It turns out that if you rearrange them, you will get dy by dx is equal to the term on the right hand side. You're understanding how this is coming from this equation? All class. Okay. Wait, I'll ask someone else. Ashwin.
Yes, sir.
I'll ask someone else. We can
Sure,
mute
sir.
right now. Yeah. If anyone of you has doubts, you can ask. Shivakumar. Shivakumar? Lakshmi Shivakumar, are you there? Yes or no? Adarsh? Adarsh,
Yes, sir.
are you understanding?
Yes, sir.
Okay. You understand this? It will be good for a lot of things. Okay. So now this happens to say that the slope of these lines is equal to something. Correct? A over dx is slope of a straight line, slope of any curve at a point x comma y. Correct? Adarsh,
Yes, sir.
this just states that the slope of the curve, if it is equal to this value, then it's a characteristic. Because our definition of characteristic is what? Set of imaginary lines along which flow variables are continuous, but the derivatives are discontinuous. When you put derivatives are discontinuous, when we assume that flow variables are continuous, UV are continuous here. Okay, but derivatives. So along these lines, derivatives are discontinuous. A by dx is discontinuous. Correct? So this is the equation of a characteristic. Any doubts so far?
Yes, sir.
So we'll stop here today. We'll continue in the next class. You can stop recording if you started. I will